Hello and welcome. In this course, we are going to explore how the role of the software developer is changing in the age of AI. Not because programming disappears, but because the way we express intent and the way tools interpret that intent is shifting dramatically. My goal is to help you express intent clearly, verify AI outputs confidently, and continue shipping reliable software. I am Will Edwards, a solution architect with 20 years of designing and building distributed systems and developer tools. This course promises that you will learn to express intent, verify AI outputs, and ship reliable code. All examples are in TypeScript, but the same can be applied for any programming language. Role of software developer in AI era, from abstraction to intent engineering. This week, we lay the foundation. We'll revisit abstraction using marketer projections. We'll walk through the history of programming abstractions, compare compilers with AI, and finally end with a short demo. Understanding abstraction is essential because AI is simply the next abstraction layer. What is an abstraction? People often say an abstraction hides complexity. That's partially true. A more accurate definition is an abstraction is a contract, a promise with constraints and trade offs. The marketer projection is a perfect example. In 16th century, sailors needed a simple way to navigate long distances. The earth is a sphere and longitudes converge at the poles. A sailor traveling from London to Miami follows a curved path and must constantly correct course. Mercator created the projection whose promise is that it preserves angles and compass bearings. It lays out longitudes as parallel lines so a sailor can draw a straight line, set the single bearing, and follow it all the way. Its constraints, it only works for constant bearing navigation. Its trade offs, it distorts area and distances. Greenland looks similar in size to Africa, when Africa is 14 times larger. Antarctica becomes enormous because the poles are stretched. The map only shows 85 degrees north to 85 degrees south because distortion becomes infinite near the poles. So you cannot rely on this map for comparing sizes or distances, but it fits its purpose beautifully, which is to let a sailor set the compass direction once and get going. Key point here is that abstraction is a contract, a promise with constraints and trade offs. Why do abstractions rise? Abstractions rise to manage human cognitive limits. Let's return to Mercator projection. Earth is enormously complex. Political boundaries, population centers, terrain, rivers, mountains, weather systems, ocean currents, flora and fauna. As a navigator, I don't need all that. I only need a way to travel from one point to another with minimal course correction. So we create an abstraction, the Mercator map, that hides most of this complexity and brings to foreground what matters for navigation. This leads to the real answer to why abstractions emerge. Not because we love elegance, but because our brains hit a wall. When the cognitive load exceeds what we can comfortably juggle, we invent a new layer. A layer that hides complexity, standardizes patterns, or encodes the intent more directly. Here are some factors that increase the cognitive load. Too many moving parts, too much variation, too much coordination, too much implicit knowledge, and too much risk. Abstractions rise because humans don't scale. Evolution of abstractions. Each abstraction raises the level of expressed intent and shifts the mental model. Before we unpack that, let's walk through the evolution of programming languages. We start with machine code. Early programmers entered raw binary or hex using hex keypads. The CPU executed those bytes directly. With assembly language, mnemonics replaced raw bytes. Assemblers translated those mnemonics into machine code. But the mental model was still very close to the hardware. With procedural languages such as C, Fortran, and Pascal, we had high-level statements, loops, and functions, which let the programmers think in steps or algorithms rather than in registers. Compilers translated these programs to machine code. With object-oriented languages such as C++, we started thinking in terms of domain-aligned objects that collaborate through messages and interfaces. Compilers still translate to lower levels, but the mental model shifts to objects and interfaces. With managed and functional languages such as C Sharp, Java, F Sharp, Scala, Haskell, runtimes emerge that provide features such as garbage collection and manage memory and safety for us. Functional programming languages emphasize pure functions and immutability. Moving on to AI generated languages. In this case, the AI generates code by predicting likely solutions rather than enforcing rules, which means developers must supply constraints and verify correctness. Across all these steps, three things happen. Complexity does not disappear, it shifts. The complexity of registers, stack frames, memory management still exists, but the compilers and runtime handle it, and we trust them to do so. The level of expressed intent rises. We express more of what we want and less of how that thing should happen. Our mental models change. We think differently because the abstraction foregrounds some concern and backgrounds others. And through all of this, one thing never changes. That's the programmer's intent. The programmer's intent is to fulfill a business requirement. Make the system do X so the business achieves Y. That is timeless. Only thing changes is the level of expressed intent and the mental models associated with that. Level of expressed intent and mental model. Let me frame this in a way that clarifies the core idea. The business requirement never changes. What changes is the level of expressed intent and the mental model behind it. These two concepts are different, and understanding the difference is essential. As programming languages evolve, this level of expressed intent moves higher and higher. It becomes less about hardware details and more about business concepts. On mental models, this is the internal part. This is the programmer's understanding of what's really happening underneath. Even when abstractions hide complexity, the programmer still needs to understand constraints, trade offs, performance implications, failure modes. The mental model never disappears, it just changes. Think of it like the Mercator map. The map is expressed intent. Knowing that the Earth is actually a sphere, that's the mental model. How do these two evolve through programming paradigms? Let's look at assembly. At this level, the expressed intent is extremely low level. You think in terms of registers, memory addresses, interrupts. Nothing resembles the business requirement. Your mental model is hardware itself. If we go to procedural languages, now you think algorithmically in terms of loops, conditionals, and functions. You still describe how to do everything. For example, when I call read, give me bytes into this buffer until end of file or until the buffer is full. The mental model still includes memory, buffers, IO, and algorithmic steps. When we move on to object-oriented languages, here the expressed intent moves closer to the domain. You think in terms of objects, their responsibilities, their interactions, not in terms of stack frames or interrupts. For example, here, when I call read CSV, it gives me a data frame. You are no longer specifying the buffer sizes or end of file loops. The abstraction has taken over. But the mental model still includes memory usage, object life cycles, copying versus referencing, performance implications, and so on. Moving on to managed languages or declarative languages, now the expressed intent becomes even more higher. You described what you want, not how you want. A single line might open a file, read it, buffer it, decode it, close it, handle retries, manage memory, all of that done implicitly. But the mental model still matters. You still need to understand immutability, lazy evaluation, concurrency models, algorithmic trade-offs, memory behavior. SQL is a perfect example. When you write order by name, you don't specify the sorting algorithm, but you still need to understand how nulls sort, how indexes work, and when memory spills happen. The key insight is that as abstractions rise, from assembly to procedural to object-oriented to declarative languages, the level of expressed intent becomes simpler and more business aligned. The mental model must remain rich because the cost of misunderstanding increases. You write less, but you must understand more. Level of expressed intent and mental model. Case study. Let's ground this discussion in a simple, fictional, real world like scenario. University of Deep Study runs an enrollment system that allows students to sign up for courses. A student wishes to enroll in the course role of software developer in AI era. Before the university can accept the enrollment, several checks must be completed. The student must have required background, example, a basic degree in computer science. The student must already be registered as a graduate student at the university. The course must be offered in the current academic year. Seats must still be available and the student must have paid the course fee. If all conditions are satisfied, the university enrolls the student and reduces the available seat count by one. The process is carried out by university administrator who logs into the system, collects the student's name and university ID and initiates the check. Now let's examine this scenario from a developer's point of view using three different programming lenses: procedural, object-oriented, and AI-generated. I'm deliberately skipping machine code and assembly. They sit too far down the abstraction ladder for what we are exploring. I'm also excluding managed language runtime features, since they don't represent a true paradigm shift in the way procedural to object-oriented to AI does. And while functional languages are important academically, they remain niche in mainstream industry. So they are not central to this case study. So we look at this problem through procedural, object-oriented, and AI-generated approaches. The key point: the business intent never changes. It is stable, technology agnostic, and expressed in plain language. What does change is how I, as a developer, express that intent. As we move from procedural to object-oriented to AI, both the level of intent and the mental model shift. Think of these as two sides of the same coin. Level of intent is outward facing, what the developer writes down, such as pseudocode, a technical spec, a Word document, or the code itself. Mental model is inward facing, the developer's internal understanding of the business problem, how he internalizes the problem, thinks about it in solution space, and builds an internal map of what the solution could look like, which abstractions and constraints are relevant, what are the moving parts, what the system should do next, and so on. The mental model is solution oriented, but it is shaped by the problem. Let's walk through it. It becomes much clearer when we see it in action. Here is the business intent in its purest form, untouched by any implementation detail. Business intent: enroll a student into a course after verifying prerequisite knowledge, student status, course availability, seat availability, and payment. If all checks pass, enroll the student and decrement the available seats. Let's start with procedural programming. Expressed intent. In procedural programming, I express my intent as a sequence of explicit steps. The pseudocode below illustrates this style. A typical function that retrieves the student by its ID, checks whether the student is registered at the university, and verifies they meet the required prerequisite criteria. Student and course are simple data structures similar to struct types in C. Functions such as getStudent and getCourse represent straightforward operations that the program performs in order. The key idea: my intent is encoded as a linear step-by-step recipe, occasionally branching out when conditions require it. My mental model: when I'm writing procedural code, I imagine the system as a flowchart brought to life. My thinking naturally follows a starting point, a series of ordered steps, branches based on conditions, loops that repeat work, a clear path from beginning to end. In other words, procedural programming encourages me to think like a flowchart designer. Control flows from one box to the next, and the programmer's behavior is the direct execution of that steps. So in my mental model, I am saying the system behaves like flowchart, so I model it that way, and I think in terms of sequences, branching, loops, and explicit control flow. Moving on to object-oriented programming, here I express my intent by assigning responsibilities to objects and letting them collaborate. Instead of writing a long sequence of steps, I describe which object should handle which part of the problem. In the enrollment example, the student object knows whether it's registered, whether it has paid, and whether it meets the prerequisites. The course object knows whether it's offered this year and whether seats are available. The enrollment service coordinates the interaction, but it does not do everything itself. It simply asks the right objects the right questions. My intent is expressed through messages. Messages like, student, tell me if you have the prerequisite. Course, tell me if you have seats. Course, reserve a seat. Each object encapsulates its own rules and data. I don't manipulate their internal state directly. I delegate. The key idea is that my intent is encoded as a set of responsibilities distributed across objects that collaborate to achieve the outcome. On the mental model side, when I think in an object-oriented way, my mental model shifts from flowchart to a collection of objects. Each object is an autonomous entity with state that it owns, such as whether is registered, available seats, payments, behavior it controls, boundaries that protect its internal state, responsibilities that define what it is in charge of, and collaborations that let it work with other objects. I don't imagine a single linear path of execution. Instead, I imagine roles interacting. The student is responsible for validating itself. The course is responsible for managing availability. The enrollment service orchestrates but does not micromanage. The system behaves like a network of cooperating agents, each doing its part. My thinking becomes, who should own this logic? Which object has the authority to answer this question? Which object should I delegate this responsibility to? This mental model encourages encapsulation, delegation, and collaboration rather than step by step control. So you can see how my expressed intent changes and how that impacts the mental model. It works both ways. My mental model also impacts my expressed intent. Level of expressed intent and mental model for AI assisted programming. Expressed intent. In AI assisted programming, I express my intent at the level of outcomes, not steps or object interactions. Instead of describing how to enroll a student or which objects to ask, I simply declare my goal or my intent. In this case, my intent is enroll a student into this course subject to these conditions. The checks here, they become the constraints. These are not instructions. The side effects, they become the post conditions and not method calls. The key idea here is my intent is encoded as a statement of desired state, and the system determines the sequence, orchestrations, and error handling required to achieve it. If you are familiar with Kubernetes, you will see the analogy. In Kubernetes, we specify the desired state and let Kubernetes figure it out how to achieve it. As per the mental model, when I'm working in an AI assisted paradigm, I no longer think in terms of flowcharts, which are procedural, or object collaboration, as in object oriented paradigm. My thinking shifts towards declaring the goal, stating the rules that must be held, describing the valid outcomes, letting the system derive the procedure, and trusting the platform to enforce constraints and maintain consistency. In other words, AI assisted programming encourages me to think like a policy designer rather than a step writer or object orchestrator. I focus on what must be true, and the system figures out how to make it true. We covered a lot of ground in previous slide. We said our thinking shifts, our mental model changes. Let's look at some examples. Declaring the intent. This is our goal. This could be enroll student with the ID 12345 into course CS 101. That's it. No steps, no checks, no orchestration, just the business intent stated plainly. This is the equivalent of telling the system, make this happen. Stating rules that must hold. The student may be enrolled only if the student exists and is registered, they meet the prerequisites, the course is offered this year, seats are available, and the fee has been paid. These are constraints, not instructions. You are not saying how to check them, only that they must be true. Describing valid outcomes. Success outcome would be something like the student is enrolled, the seat count is reduced by one, enrollment record is created, and a confirmation is message is sent. Failure outcome would be no enrollment occurs, no seat count changes, a message is returned explaining which rule failed. You are defining the shape of the result, not the steps to produce it. Let the system derive the procedure. You don't specify first check for prerequisites, then check for payment, then check seats, and then update the database. Instead, you trust the system to figure out the correct order, the dependencies, error handling, rollback behavior, data access strategy, and so on. The system decides on how based on your what. Trusting the platform to enforce constraints and maintain consistency. You don't write code to prevent double enrollment or race conditions. You simply state seat count must never go below zero. A student cannot be enrolled twice in the same course in same year. And the platform ensures concurrency safety, transactional integrity, consistent state transitions, correct sequencing, error propagation, and so on. Your mental model becomes if I state the rules clearly, the system will uphold them. Let's explore one of the most important shifts in modern software development. AI is becoming the new compiler. For decades, developers told machines how to do things. But now we tell AI what we want and it figures out the how. Let's start with something familiar. A traditional compiler takes precise instructions in a strict grammar with no ambiguity. It creates an abstract syntax tree internally to validate the input against the grammar. It generates machine code only when syntactically the instructions are correct. A compiler is deterministic and has a predictable output. Output is machine code. When we say deterministic, I mean the compiler will generate the same code every time you give it the same source code. There is no randomness, there is no surprises, there are no variations. If your syntax is wrong, the compiler refuses to proceed. If your logic is incomplete, the compiler does not guess. AI doesn't behave like that. AI reads natural language, which is vague intent. It accepts diagrams, examples, partial descriptions, and it makes assumptions. It fills in gaps, that is, it guesses the missing details. It improvises even with incomplete, ambiguous, and conflicting input. It's important to note that AI is eager to comply and generate an output, and that AI is creative. AI uses probabilistic models and can produce unpredictable output. Output is the source code and other artifacts. Important to note that it fills in gaps. It makes assumptions. It generates structure and improvises. That's why AI is powerful and yet it is dangerous. It is creative but not guaranteed to be correct. Your job as a modern developer is shifting. You are no longer just writing code, you are designing intent. You are shaping the inputs that guide the AI. You are validating the outputs. This is why clarity, constraints, domain modeling, and boundaries matter more than ever. Why intent engineering matters. We know that AI can fill in gaps, make assumptions, and is eager to produce output. Let us put this to test. For this exercise, I selected Claude HiQ 4.5 on GitHub. I gave it a vague intent. Build a course enrollment system for students. Nothing else. No validations, no constraints, no business rules, no workflows, error handling, or domain modeling. Claude produced 5 files: the main controller, a test script, and 3 domain classes: student, course, and enrollment system, just as I expected. Since I primarily use TypeScript, Claude assumed I wanted the output in TypeScript. This is fine. Here are the files. You can check them out on GitHub as well. The student class looks all right. It's got an ID, a name, an email. The constructor verifies, checks whether these fields are empty or null, and if not, it throws an error. And there are a set of getter methods along with toString. Course also is quite similar. It holds the ID of the course, the name of the course, what the capacity of the course is, and the listing of students which are enrolled for that course. Again, it's got a constructor which does basic checks, has a series of getter methods, and a method here called enroll student, which is smart. Uh, Basically, before it enrolls the students, it checks whether the student is already enrolled and whether the course has a capacity to enroll the student, which is good. If we look at the enrollment system itself, it has a map of students, or I would say a list of students. The map is between the student ID and the student object. Likewise for courses and the mapping of students to courses. It has constructors, it has various methods like register student, create course, but this one is interesting, enroll student, because this one is quite smart. Um, it gets the student, then it gets the course, checks whether the student is already enrolled in the course. If not, then it enrolls the student into the course. And if that fails, then it throws an error. Likewise, we have a drop student, get students in course, and a lot of other functions. They're all quite good. These two I mentioned, these are just for tests, so I'm not going to go into them. They all look pretty good. Let's look at what Claude did well. The code is clean, it's readable TypeScript, it's got good naming, clear method signatures, it does not have unnecessary complexity, and it has a reasonable separation of concerns in terms of how it's structured the classes. There is sensible domain modeling. Student and course are simple, well encapsulated classes. The enrollment system acts as the coordinator, similar to our enrollment service. The demo script is structured and readable. There is basic error handling. The code does check for duplicate students, duplicate courses, checks whether the course has the capacity to enroll student, um, and does various other kinds of checks like missing students and courses. The output is surprisingly polished. It's a step-by-step narrative, clear console outputs. It demonstrates the success and failure paths. In short, Claude produced code that is clean, coherent, and logically structured. Well, this looks great. What's the problem? The code produced is fundamentally shallow. Why do I say that? The system models only the simplest possible enrollment rule. As long as there is surplus capacity, enroll the student. But the real world is full of constraints. All of those are missing. Some rules or constraints are: a student must have prerequisite qualifications. What about timetable clashes? There are enrollment windows during which students can enroll. There are program and year restrictions. Some courses may not be available all year round. What about waiting list? There is no concept of that. A course status could be open, closed, or cancelled. Not there. A course will earn students some credits per term. There is no mention of that. A real enrollment system is policy heavy. Claude implemented just one policy on capacity. Student accepts invalid emails, duplicate emails, malformed IDs, empty names with white spaces, names with numbers. Everything in the enrollment system throws an error. This is fine for a simple demo or for a proof of concept, but terrible in production systems. There is no hierarchy of exceptions. There is no persistence. There is no boundaries. There are no repositories. Everything is in memory. Again, fine for a demo, but in real world, we need persistence, we need transaction boundaries, we need protection from concurrency, just to name a few. The code assumes a single-threaded model where there are no concurrency issues. The demo here only uses valid data, only goes through the happy paths. It never tests edge cases, never tests invalid format, never tests concurrency or domain rules because there are none. This gives us a false sense of correctness. Code generated by AI is good for teaching basic object-oriented programming, for demonstrating AI generated code structure, for showing readable TypeScript, for illustrating happy path logic. But it's not fit for real enrollment system. A system that has policies, systems that has persistence, and systems that have to deal with concurrency. This is where you, the developer, come in and shine. Key takeaway. The key takeaway for this section is that AI is not magic. AI is not a compiler either, but AI can behave more like a compiler when the intent is structured. Developers' job is shifting from writing code to designing intent. Domain modeling and constraints matter more than syntax. To summarize it, AI is not replacing developers, it's replacing the low level translation of intent into code. Your value is shifting upwards towards modeling, clarity, and intent. Think of AI like a junior developer who never says, I don't understand. It will always produce something, even if it is wrong. Your job is to give it the clarity. That brings us to the end of week one. I know today's material was intense, dense, and quite conceptual, but that's intentional. This course is designed to give you an early understanding of the shifts already reshaping software development. As we move through the coming weeks, the ideas you have seen today will start to connect, and the bigger picture will become clearer and more practical. If you found this session valuable, consider subscribing and giving it a like. It genuinely helps me continue creating content like this. My goal, as always, is to equip you for the next decade of software development in an industry being transformed by AI. Thank you.